This video in 10 words: improved PCI, attempted Rust, attempted IDE, next steps, AHCI, SATA. But first, what is PKOS? Our entire world runs on computers, but few understand how they work at the lowest level. Everything from your phone and laptop to the flight controllers on an airliner has at least one computer chip in it called the CPU, which tells it what to do. The operating system is supposed to handle all of the low-level operations, including interfacing with hardware. But what does that interface actually look like? It's easy enough to write a file using file.write in Python, but this is just an abstraction for what's really happening. Somewhere under the covers of layers and layers of abstraction, there's a metal disk spinning or a solid-state drive, and you're rearranging zeros and ones on that drive. In this series, we throw away all of these comfortable abstractions that are provided to us and do bare metal programming. Our code runs directly on the processor. There's no standard library, no system calls, and no API other than the processor itself. If figuring out how to make things happen with only the processor and nothing else sounds exciting to you, then this series is for you. PKOS stands for PageKey Operating System, which is an operating system built from scratch on video with each lesson learned along the way explained so that you can easily understand it and apply it to your own projects. In this lesson, we continue our exploration of PCI, clean up the code base a bit, attempt unsuccessfully to use Rust, and begin researching how to write a storage device driver. What we did. Here's a quick summary of what was accomplished since the last video. The most important additions will be expanded upon in the deep dive section below. Lessons learned. Working through the code for this video yielded a ton of great lessons. Here's what I found. Structs are wonderful. I was dragging my feet on implementing a struct to hold the PCI device data I was grabbing from the configuration memory, but I was amazed at how easy it was to do and how much cleaner the code got when I did it. Just look at this lovely little struct. With this in place, I was able to abstract away all of the bit shifting that was required to get this data from the PCI configuration memory and just return the finished object. This made the implementation of LSPCI much cleaner and easier to read, and it will avoid duplicating code when we write the storage device driver. PCI Class and Subclass. Every PCI device has a vendor ID and a device ID, and you can use these two numbers to look up exactly what the device is. Just type it in on PCILookup.com and see what you come up with. Rust bare metal i686 support is dodgy. I was sad to find that 32-bit x86, also known as i386 or i686, does not have the best support in Rust for bare metal programming. There is no default i686 unknown none toolchain, which means that you have to define your own based off of the i686 unknown Linux GNU. I tried my best but couldn't seem to get a multi-boot kernel to compile. I'd love to use Rust if I could figure it out, but it wasn't in the cards for this episode, so we'll stick to the simplicity of C for now. Storage drivers. IDE, PATA, and HCI, SATA, are very different. I spent a fair amount of time trying to get the IDE controller that was attached to QEMU by default working. I'm not sure if it's actually what I need. It seemed to be a CD-ROM drive. From what I gathered, IDE/PATA is no longer used for hard drives, but may still be used for CDs. SATA and HCI, on the other hand, are still very much relevant. We'll go into this in more detail soon. Deep dives. Let's dive into the details of the code for this episode. Parsing PCI fields into struct. The PCI configuration memory layout was essential in figuring out how to parse the fields. Recall that we have a working read PCI port function at our disposal, and it takes 4 single-byte arguments: bus, slot, function, and offset. For a given PCI device, we can make multiple calls to this function, changing the offset field to grab the variables that we want out of the structure above. For example, here's a snippet of how we get the vendor and device ID. As you can see, we grab 32 bits at offset 0, then bit shift or AND the result until we isolate the fields that we need. Check out this early look at the LSPCI method. Looks great. The only problem is that there are quite a few devices with the vendor ID PPPP. That can't be right, so what's going on here? Ignoring non-existent PCI devices. The Linux kernel finds non-existent PCI devices by checking if the PCI class field is set to all ones. OSDev mentions that you can also check whether the vendor ID field is set to all ones. Though both probably work, I went with the latter technique. Applying this knowledge will save our LSPCI function some work by skipping any further processing when it detects a non-existent device. Now we only see a few devices, and none of them have invalid fields for vendor ID anymore. Looking up PCI devices. Looking at the above screenshot, how much can you tell about the devices listed? At first, I had no clue where to start with deciphering these fields. However, a quick search showed me that I can use PCILookup.com to find out what each of those devices are. For example, looking up vendor ID 8086 and device 7010 yields the following. This matches with QEMU documentation and with the output of info QTree, so it seems like our LSPCI method is accurate. PCI base class, subclass, and programming interfaces. The PCI fields list above shows one big 3-byte chunk for class code, but documentation sometimes referred to the subclass field, which I couldn't seem to find anywhere. However, it did seem to be a powerful way to tell what type of device you were dealing with. As an example, class 1 indicates a mass storage device, and class 1 subclass 1 indicates an IDE interface. The specification documents for PCI don't seem to be freely available online. You have to log into PCI SIG's website to download any of them. However, someone hosted the PCI local bus specification from 2004 on their website, so I was able to take a look. On page 217, it tells us that the class code register is read-only. It's broken into 3 byte-sized fields. The upper byte at offset 0B is a base class code. The middle byte at 0A is the subclass code, and the lower byte is the programming interface. So that's simple enough. We can parse those fields with this snippet of code. I cheated a little bit by reading with offset 0x09 to save some bit shifting, as opposed to reading on the 4-byte boundary at 0x08. There's probably some kind of performance impact for this, but for our OS, I don't think it matters. Attempts to use Rust. I attempted to create a multi-boot i386 kernel using Rust. If I had been successful, I could have linked in all of the existing C and assembly code into that executable, and any new development could have been in Rust. Unfortunately, I hit some roadblocks. A Stack Overflow answer by FIP1611 informed me that while there's no built-in target for bare metal 32-bit x86 code, you can define a custom target by putting a JSON file at the root of the project and pointing to it in .cargo/config.toml. Using the noStandard and noMain macros turn off the standard library and main method, which enable bare metal execution. I also found an awesome tutorial called Writing an OS in Rust, which explained each piece of the puzzle very clearly. However, the whole tutorial was written for x86-64. Maybe the time to upgrade PKOS is coming, but I'm not ready to let go of 32-bit yet. After messing with Xargo for cross-compiling for quite a while, I finally gave up on this path for now. What is IDE? IDE stands for Integrated Drive Electronics. It's an electrical standard for disk storage devices released in 1990. It was originally referred to as an Advanced Technology Attachment, or ATA, but after the introduction of Serial ATA, or SATA, it was renamed to Parallel ATA, PATA. We can identify IDE devices using the class code field in the PCI configuration space. OS Dev Wiki tells us that if class code is 0x1 and subclass is 0x1, then it's an IDE controller. This takes care of the first two fields, but what about that pesky programming interface byte? I found something that said it's used to indicate whether the primary and secondary storage devices are programmable, as well as their operating mode. I was able to find the specification for a PCI IDE card online, and I particularly enjoyed seeing that the class codes matched up with what I'd seen from other sources. Another potentially helpful resource was a guide for writing an IDE driver from the RTEM's Real-Time Operating Systems documentation. I was also able to find the source code for it on GitHub. It seems like the ATA driver in ata.c uses perhaps the lower level functionality in IDE controller.c. Not really sure exactly what's going on there, but figured I'd include it as a resource. RTEMS also provides a separate guide for writing an ATA driver. The OS Dev Wiki has one too. This is a little confusing to me because the Tech Target article that I saw seems to indicate that ATA and IDE are basically interchangeable. What is SATA? SATA stands for Serial Advanced Technology Attachment, defined as noted above in contrast to IDE and PATA. AHCI stands for Advanced Host Controller Interface. I've seen these two acronyms used interchangeably in some of the drivers I saw online. However, Dell indicates that it may be more complicated to support an AHCI device than a SATA device. I'm not sure how true this is. Adding SATA to QEMU. One Stack Overflow answer told us exactly how to explicitly add a SATA device to QEMU. I appended these lines to the os.py script's run and run debug methods, and lo and behold, the SATA drive appeared in LSPCI. It's on bus 0, device 4, function 0 in this image. Ruben Shade highlighted a similar technique for adding the drive in his blog. It also seems like it may have been enough to simply use the -HDA flag on the QEMU run command, but since I did it the more complicated way first, I just went with it. Even though I didn't quite get as far as I'd hoped in this episode, I still made some progress and learned a lot. Hope you enjoyed it and learned something too. Next steps for this project will likely be to get some sort of SATA driver working, though from what I've seen so far I'm a little intimidated by how complex it can get. We'll see how it goes. If you enjoyed this post, consider subscribing to the PageKey YouTube channel. Thanks for watching.